I have Adam. Adam, how do you pronounce your family name?
Yeah, so Adam Konopka.
Good, thank you. I'm going to ask you questions. You can answer them any way you would like, including you can demur. Adam, where were you born?
Yep, so I'm from Aurora, Illinois. I got a little spiel in there about some of my background, so I'll share some of that to kind of just help you get to know me.
Good. So you were born in Aurora, and where'd you go to high school?
West Aurora High School.
And then where'd you go for your undergrad and what'd you study?
Yep, so I'm going to go over all this.
I know, this is our standard.
Okay. Yeah, so I went to Ball State University.
Oh.
So that's in East Central Indiana. Famous alumni are David Letterman. So I went there for undergrad and graduate school.
Excellent.
Yeah.
And then where'd you do your postdocs?
I did postdoc at Mayo Clinic and then Colorado State University.
How'd you like Fort Collins?
Loved it, but
how do you compare the skiing there compared to like Rochester?
I'm not a big skier, so I can't really answer that question. I love being in the mountains, but actually I think I would prefer Madison over Colorado.
Wow.
Yeah.
He fell and hit his head as a young child. So, well, thank you very much for talking today about rapamycin, is that correct? And mTOR, I don't know what that is. But this is going to be cool stuff. Would you please join me in welcoming Adam to PLATO?
Thanks so much. Yeah, well, it's really an honor to be here. When someone was trying to reach out about trying to discuss some rapamycin clinical trials, it's like, well, what a better couldn't have a better opportunity, really. And I'm going to talk about some of the background that have led to some of the rationale and the objectives of our clinical trials, and then also, share briefly a high-level overview of what we're trying to accomplish. I guess one of the neat things is there's probably about 6 to 8 different clinical trials across the world, and we have 2 of them right here at UW-Madison. So I think that's really a unique aspect, and I think that really showcases the value and just the rich history that the Division of Geriatrics has at UW-Madison and the Department of Medicine. And so I think that really just, I think it's an outstanding environment to work, and it's been a really honor to be here. We have a lab website. I have failed to update it recently, but we do have a lab website. You can feel free to check out for more information. And then we are on Twitter if you are into the social media thing. So without further ado, let's get started. So the reason I'm here is we're really interested in how we can age and how we can age in a healthy manner. And so we know, based off of a lot of the epidemiological data, that chronological age is one of the greatest risk factors for nearly every chronic condition that you can think of. And so we see that illustrated here just as disease incidence rates. So how fast people, develop these different diseases, if you will. And you can pick your favorite disease to study. That's why I tell my colleagues that aren't, directly in geriatrics, but you can pick your challenge or condition and whatever it might be, and there's going to be some sort of age-related increase. It might have a different, shape to it, but in general, it's going to go up with age. And this is concerning because as our population is aging, we're expected to have over 2 billion individuals over the age of 65 in the next 20, 30 years. And on top of that, rarely, it's about over the 50% of the population of 65 years and older actually have 2 or more chronic conditions. So it's rare that there might be some sort of single issue to try to treat. It's actually multiple conditions. And so our idea, and again, you pick your condition and it's going to have this age-related increase. And so our philosophy, or kind of our hypothesis with the field, is that we really need to start thinking about how we can intervene on the biology of aging that drives this sort of dysfunction that increases our risk for these age-related chronic conditions, right? So we're targeting aging as a whole, as an umbrella, because if we start targeting just one disease at a time, there's some value to that, obviously, but when we're talking about extending our healthy longevity, we think we can have greater dividends by targeting the underlying mechanisms of aging rather than these individual diseases. And so today, the objectives are, to establish the impact of age on chronic conditions that we just did. I'm going to give you a little background, a little bit more in detail than what we went off or how we started. I'll talk about what is called this geroscience hypothesis, and then kind of the research approach that we take to kind of test this hypothesis to some degree. And then we'll talk at the end about rapamycin and how potentially that could be a medication that could potentially increase healthy longevity. So me, as we discussed, so I'm originally from a suburb of Chicago, Aurora, Illinois. It's similar size as Madison, has a lot of actually similarities, I would say. After that, I went to Ball State University. I was a swimmer growing up, and I got a swimming scholarship to continue that athletic pursuit in Muncie, Indiana. And you stare at the bottom of the pool long enough, you start wondering what's going on with your own body, right? And so my focus area of study was exercise physiology and bioenergetics. And so I did my undergrad and graduate training in the Human Performance Lab at Ball State. It's one of the highly regarded human performance centers in the country for biomedical research. And so I was really focused on sarcopenia, which is the age-related loss of muscle mass and function. And so what are some different, exercise and dietary approaches we can do to help slow the decrease in muscle size and try to maintain physical function throughout life. From there, I went to Mayo Clinic in Rochester, Minnesota. I've never been more cold in my life. Even from Chicago and even in Madison, I think it's still colder and more snow up in Minnesota than here. So I was there for 2.5 years, and I was in the endocrine research unit at Mayo Clinic. That's in St. Mary's Hospital for anyone who is familiar with that campus. And so we still studied a lot of aging-related issues, but it was more focused on insulin resistance and glucose homeostasis. And so that kind of makes sense thinking about how those are risk factors for diabetes and why we were in the endocrine research unit. But I learned a lot of really great techniques there that I still employ today here at UW-Madison. So it was a very valuable training opportunity. And then I moved out to the West. So the first time out of the Midwest and out to the mountains, and it was beautiful. I had an office. I could see a 14,000 foot peak from my office, which was really special. And there I worked with Benjamin Miller. And I think the greatest thing there is I learned a lot from research, but also a lot in professional development. So how to, mentor students, how to run a laboratory, things that you don't really have a class that teaches you that, you kind of got to figure it out on your own. And so those career development opportunities were priceless. I was able to secure a faculty position at the University of Illinois down in Champaign, Illinois, which is about 2 hours south of Chicago. So I was there for 3 years, and then I was recruited here. And I have no desire to move ever again. I'm very happy here. Love all the 4 seasons, even the winter, even though it's long. And so this is really where home is now, and it's been just a really fabulous opportunity. We have an ongoing clinical trial now, and so just to kind of get to meet some of the community members and really how passionate they are about moving science forward is great. It actually reminds me a lot of being in Rochester, where there's a lot of commitment to helping Mayo Clinic progress in their biomedical research. I have a lot of sense of that same pride here in Madison, and I think it's fabulous. So it's one of the best things as a human researcher we can ask for, is have that buy-in from the community. So this is the geroscience hypothesis. And so this is kind of the connection between the fundamental biology and some outcomes that might be more clinically relatable. And so the idea is that there are a handful of different biological processes that are all interrelated. So, they're listed here, and you can kind of see they're all connected in this web. And so it's not just one aspect of aging that becomes dysregulated or impaired at some degree. It's all of these things collectively that contribute to a decline in physiological function. And so that's the aging physiology part. So as we have that age-related decline in physiological function, even if you're a healthy individual, you can still notice some of these declines. And that really increases our risk of developing what we call these age-related chronic diseases or conditions. Either some in the room or even friends probably can relate to a lot of some of these issues. And so our goal, again, it goes back to the idea that if we can improve and target maybe one of these kind of biological mechanisms, then perhaps we can help restore a lot of their neighboring biological processes to help maintain physiological function as we age. So that's kind of the concept. And the way that we really attack this is we use a translational, what we call a translational geroscience approach. And so what that means is we have studies in cell culture dishes, we have them in mice and other rodents, and we can manipulate a lot of these biological variables. And we or others in the field have shown that when you do that, you can actually modify lifespan. So you can actually make these animals live longer, which is really great. But we don't really care so much if we can make a mouse live long, right? Like that's very fascinating and we love the biology behind it, but that doesn't really do much for you or I. And so our goal is to take those findings and try to apply them up the kind of translational scale. So we have some studies in non-human primates, and then eventually we get to human clinical trials. So we can test whether or not different strategies are safe and effective at kind of extending this healthy longevity concept. And University of Madison is actually really unique because we have a great infrastructure where we're eventually, if we're successful at showing whether that's exercise or medications or et cetera, that can extend this healthy lifespan, we have this community resource where we're able to actually get into different communities and neighborhoods across Madison, regardless of social economical status, and hopefully make these treatments and therapies accessible to everyone. And so this is just another conceptual framework. So there's some limitations of this, but I think what's nice is I think people can actually visualize and kind of conceptualize what we're trying to accomplish here. Is my goal personally is not to make people live forever. I'm not really motivated behind that. I'm not sure if people want to live a very, very long time, especially if they're trying to manage different diseases or disabilities. And so what we're really focused on is this concept called health span. So that's up here and that's in the green. And that's where we as a group are just, we're functionally able to do just about anything. We have very few limitations. We don't have any chronic conditions or diseases. And so our goal is really try to extend this health span for as long as we can. Because we know with increasing age, we have that decline in different functional outcomes, and that increases our risk for these diseases and disabilities. But if we can intervene before these different conditions, then perhaps we can actually successfully extend health span and limit that time spent with different disease states. So basically the idea is, how can we extend quality of life and vitality all the way to the end? And there's a handful of different approaches that have been studied. And I'm going to talk mostly about rapamycin today. But by far and large, the human data is most convincing for exercise. So right now you can't beat exercise. That's the gold standard way to improve or maintain a healthy longevity. There's some dietary approaches that have worked well, and there's also metformin. We have another clinical trial using metformin right now. I would say those are more equivocal than rapamycin. And so the field as a whole is very excited about using rapamycin as a potential strategy to increase healthy longevity. So to start, we need to just talk about the molecular target of rapamycin, which is the mechanistic target of rapamycin. And so this protein, it's a kinase. So kinases phosphorylate downstream proteins. So when you phosphorylate a downstream target protein, you can either activate it or deactivate it. So you can kind of think of it as light switches throughout your house that you're turning on and off to regulate these different pathways and processes. And so mTOR has its hands in just about everything in the human body. All metabolic processes mTOR is involved in. And mTOR exists in two distinct complexes: mTOR complex 1, which I'll refer to as mTORC1, and then mTORC2. It's the second complex. And so you can see that they have a host of shared and distinct common subunits, specifically that mTOR protein. All right, and so there's just, I think it will be important as we move forward to keep in mind that there are two different types of mTOR, complex 1 and complex 2. So rapamycin is FDA approved. It's Treatment indication is for kidney transplant. So it helps prevent rejection of that new kidney. And it's also used as a chemotherapy agent in some cancers. It was originally actually discovered in the soil on Easter Island. And now obviously it's synthesized and made now, but when they found it, they were studying a variety of different biological processes, but they found that this compound inhibited mTOR. And so they named that protein mTOR based off of the function that it has through rapamycin. And so the way rapamycin works is it inhibits mTOR signaling. All right, so it almost immediately will inhibit mTOR complex 1. So it's very potent, and it does so even in acute circumstances. When we give rapamycin for prolonged periods of time on a daily basis, then that can also lead to an inhibition of mTORC2 signaling. All right, so mTORC1 is its primary mechanism of action, but we can have off-target effects when we give it for long periods of time on a daily basis on mTORC2. And there's research for the past 20 years, they've used rapamycin in a bunch of different model systems. So it's flies, worms, mice, rats. There's some ongoing studies in dogs and monkeys right now. And all the data so far suggest that rapamycin can extend the lifespan of all these model systems. And it's not just been done in one lab, it's been done in multiple labs across the country, across the world, right? So it's one of this, it's repeatable. It's probably the most rigorously tested pharmacological approach, and it seems to be true in just about everything that's been tested so far. Yep.
It also shows a decrease in all kinds of diseases, the cancer in dogs and other. Most
model systems where they've, and I'll review a couple, but most kind of conditions, there's been improvement. So meaning, and it can be a few different things. It can help maintain, so you prevent the loss as we get older. It can improve, so it can increase whatever variable or pathology that you're looking at, or it can actually restore. So it can actually rescue some age-related impairments, which I think is absolutely fascinating. That's only been shown in the heart, but I think that it was very provocative and pretty powerful data. And so here's just one example of extending lifespan. The National Institute on Aging sponsors this program called the Interventions Testing Program. And it's located at 3 different sites across the country at Michigan, Texas, and Maine. And so they have this spread out to try to basically account for the variability, site to site, to make sure that this is a very rigorous approach throughout the country, different locations, et cetera. And these are the pooled data, so from all 3 sites. And what they've shown is that in both males and females, that rapamycin can extend the lifespan of mice. And these are heterogeneous outbred mice, so there's a little bit more variability than your standard laboratory mouse, the goal being that hopefully that reflects some of the variability that we see in humans. And they've shown that not only does it extend lifespan when you started at a younger age, but also if you started at an older age, it can still be effective at making these mice live longer. Also been shown in models of obesity and some other kind of disease-specific models as well. And so in addition to lifespan, it also has the ability to delay several pathologies. And it can also, when dosed appropriately, can improve different indices of physiological function. And there's also a downside, and we'll get to that next. But there's data to suggest when rapamycin is given acutely, it can actually improve insulin sensitivity or glucose uptake in humans. These are in young men, so I will preface that. But insulin sensitivity, if you have a lower insulin sensitivity, that's putting you at risk for developing prediabetes and type 2 diabetes. So improving insulin sensitivity would be a favorable outcome. When rapamycin was started later in life in mice, it was actually shown to reverse some of these pre-existing age-related heart dysfunction. So that was probably the most, I think, profound outcome where it could actually restore cardiac function. When started late in life and only given for 3 months, The data suggests that rapamycin can slow the loss of physical function. So the mice didn't have quite as a decline in their grip strength and in their running performance. So hopefully it can slow down some of those outcomes. Dementia-related outcomes, I think very important to a lot of folks, both in normative aging as well as models of Alzheimer's disease. Rapamycin has been shown to restore some of the vascular function and blood flow, which is an early biomarker for Alzheimer's disease, and actually improve cognitive performance in these rodent species. So again, a pretty compelling argument. There's an ongoing clinical trial in Texas who is actually studying rapamycin in humans to see if it can have some benefits in humans related to those with mild cognitive impairment and early Alzheimer's. And then last, it actually improves immune function. And so both in mice and in humans, a six-week treatment of the rapamycin analog called everolimus was actually shown to boost older adults and older mice, their response to the influenza vaccine. And so there's also some ideas or hopes that it could also improve the vaccine response for other diseases like COVID, for example. There's several COVID-related trials going on right now, trying to use this drug to help kind of rejuvenate and restore immune response to different individuals who might be at risk from suffering long COVID or other kind of COVID-related issues. So I painted this picture that rapamycin is kind of this holy grail, and it's this, amazing drug, which I think it is, that has a lot of promise, but there, just like every medication, there are side effects, right? And so I think the side effects of what, and the fear of the side effects are what really has stalled, I think, the wide use of rapamycin for aging related outcomes. And so, and I should note that most of these side effects occur when they're given at high doses that are used for its treatment indication, right? So you have to use high doses to try to treat cancer, to try to attack the tumors from growing and metastasis. And you also have to use high doses with kidney transplant. But we don't necessarily need those high doses for what we are doing. And I'll show you some data to suggest that. So most of these are related to the dose. And so there's I talked about how on one side, on the left, if we give rapamycin acutely, it can improve insulin sensitivity. But on the right here, if we give it for prolonged periods of time at high doses, that's when we can cause hyperglycemia, new onset diabetes, dyslipidemia. And I would say the most common side effects are the last two. Some people develop transient mild mouth ulcers. They tend to go away after a couple of weeks. I'm not entirely sure the mechanisms for why that is, but probably has to do with something with the immune system. And then infections. So while, after humans take the drug, it can improve their immune function. But while they're actually actively on the drug at high doses, it can actually increase your risk of infections. So what people have shown is people have a higher chance of catching a cold or other type of illness when they're on the active study drug at high doses. I will say that most of these adverse side effects are minimized by some of the dosing schemes that we are trying to employ in our clinical trials, and that others are starting to adapt as well.
How do you think this works?
This is orally. So this is a capsule. It's a small capsule. It's 8 by 8 millimeters. So it's less than a centimeter big. We'll get into that. Yeah. So the FDA label for the indications are anywhere from 2 to 5 milligrams per day. And then there's everolimus, which is a rapamycin analog. Sometimes there's recommendations for up to 10 milligrams per day, which is very high. We'll get into that. So this is our working model, and it comes back to the two mTOR complexes, right? So we know that when we give rapamycin acutely, it can inhibit mTORC1. When we give it chronically at high doses for a prolonged period of time, it can also inhibit mTOR complex 2. Work from my colleague here at University of Wisconsin-Madison, Dudley Lamming. He's an expert in a lot of the mouse work that has really, I think, propelled and motivated the field to do clinical trials. He used different genetic strategies to disrupt the mTOR complex 1 signaling cascade. and showed that it replicated a lot of the benefits that we see with rapamycin. It increased lifespan, and it increased a lot of physiological outcomes, and so overall improved what we call that health span. Did the same thing where they used genetic approaches to selectively disrupt mTOR complex 2 signaling, and actually showed a lot of detrimental outcomes. There was increased frailty, there was metabolic disturbances, and shorter lifespan. So the thought process here is that we want to inhibit mTOR complex 1 because that's related to improved health and longevity, but we don't want to inhibit complex 2 because that's related to a lot of negative outcomes. So when we were designing our clinical trial, we were trying to think of dosing schemes that we can preferentially inhibit mTOR complex 2 for those beneficial outcomes on lifespan, and then minimize our impact on mTOR complex 2 to minimize those risk of adverse events. So that's very important for us moving forward, because I'm kind of in that mindset that I don't want to ask someone to partake in a study if it's going to put them at undue risk, right? If I wouldn't do it, then I'm not going to ask anyone else to do it. So I want to make sure that we're trying to find the safest dosing schemes possible for people to take. And so some of the data stem from some of the work in mice by my colleague Dudley Lamming. In this first study, they were looking at different rapamycin and rapamycin analogs. So we have rapamycin here in the black bar, we have everolimus, and then we have temsirolimus. So these are just different kind of derivatives of rapamycin. And again, sure enough, we show that all of these drugs largely inhibit mTOR complex 1 signaling, which is we're measuring a downstream target that of mTOR complex 1 S6 kinase. And so that would be related to positive outcomes, right? And then they looked at mTOR complex 2 signaling, which, remember, if we inhibit mTOR complex 2, that would be related to negative outcomes, right? So that's where that negative sign is. With rapamycin given every single day, we show a 50% inhibition of mTOR complex 2. So that would not be what we want. But what was found here is that everolimus, this analog, actually doesn't have quite as big of an impact. It's not even statistically significant. So it has a less impact on mTOR complex 2. So this is good. So everolimus seems to be preferentially inhibiting mTOR 2 with minimal disruption of mTOR. Is preferentially inhibiting mTOR complex 1 with minimal disruption of mTOR complex 2. So this is a compound that we think perhaps could be used in a safer manner, perhaps than just rapamycin. And not to say that rapamycin can't be used safely, because I think it can, and that comes from this figure. And so this next study, what they were comparing is the impact of rapamycin given once every day or once every week. And when they were doing the weekly dosing scheme, they tested the mTOR signaling cascade 1 day after the last dose and 3 days after the last dose. And so what they showed is that whether you give it once a day or once a week, you have a very substantial decrease in mTORC1 signaling. And then after 3 days, this starts to recover. And there's other data to suggest that 4 to 5, 6 days later, it's back towards its baseline resting level, right? So the impact on mTOR complex 1 is transient, and then it starts to recover. Then when they looked at mTOR complex 2, found the same design where rapamycin was given once per day or once weekly. They showed that the once per day, again, had about that 50% decrease in mTOR2 signaling, which would not be favorable. But when we give it once every week, we basically avoid that, right? So there are some kinetics that are involved with mTOR signaling where we think that we can more preferentially and selectively inhibit mTOR complex 1 without having mTOR complex 2 if we give it on a more of a weekly dosing scheme rather than a daily scheme, right? So the daily dosing is related, associated with a lot of off-target effects, but we think the weekly dosing scheme may be better. And that's supported here as in this study, they were trying to find the most frequent dosing scheme that they could, or dose that they could give without having some of these metabolic impairments. And so this is a glucose tolerance test, very similar to an oral glucose tolerance test. That's a somewhat common clinical outcome in individuals. And so what they were doing is they were comparing a vehicle control, so basically your placebo. And then they were given rapamycin once every 5 days and rapamycin once every 3 days. And they showed that when you give it once every 3 days, you start to get these metabolic impairments. So higher values here are related to impaired glucose tolerance. But if you give it once every 5 days, you kind of avoid those negative side effects, right? So again, it goes back to this, perhaps intermittent dosing regimens might be a safer approach for us to test in the clinic. Then they went on to do a small lifespan study. These are not easy to do. They actually take a lot of resources and a lot of time and dedication. And they showed that at least in female mice, that this once every 5 days of rapamycin still was able to extend lifespan. So when that curve is shifted to the right, that's a longer life. And did so without having a lot of these metabolic disruptions that they see with daily dosing, right? So it's still effective, but it was a little bit safer to do it on a weekly or intermittent dosing schedule. And so that's the take home here. So one of the first in human studies was done by Joan Manick when she was working for Novartis. Novartis makes everolimus, which is a rapamycin analog. And so they were testing how 6 weeks of everolimus, whether it could improve vaccine efficacy. And I kind of already showed in the slide earlier that it does, but these are the data. So the primary endpoint for this study was an increase in 1.2-fold titer response to 2 of the 3 vaccine strains. So basically you get a flu shot and then they measure the antibody response to these different vaccine strains. And this is based off of previous data to suggest that 1.2-fold greater increase versus the placebo actually has some clinically relevant outcomes. And what they found was that when everolimus was given at 0.5 milligrams per day, which is a very low dose, or given at 5 milligrams per week, it met the primary outcome above that dark black line, where it increased the flu response by greater than 1.2-fold in 2 of the 3 vaccine strains. The highest weekly dosing, so 20 milligrams per week, did not meet the primary outcome. They did some pharmacokinetic, pharmacodynamic modeling, and they showed that the effective doses attenuated the mTOR1 signaling by 38 to 50%. And it did so relatively safely, which I think is another extremely important thing to remember. There was no differences in serious adverse events. So serious adverse events would be hospitalization, death. Those are usually the big ones. So there's no difference there. The most common side effects reported in these low daily and low weekly doses were those transient mild ulcers. So about 11% of the population experienced those versus 2% in the placebo. There was an increase in total cholesterol and LDL, so often viewed as the bad cholesterol, and that happened in 7% of the treatment groups versus 0% in the placebo. So there are risks. Some view these as low because it's only 11% or 7%, but I think everyone can make their own judgment there. And so the other thing to keep in mind is, so that was just for the low daily and the low weekly. The 20 milligram weekly dosing scheme actually doubled the amount of adverse events. So in our minds, just ethically, I suppose, but even just, we wouldn't want people to take 20 milligrams per week. And so we have designed some studies and we're staying well below that 20 milligram per week because it increased the occurrence of adverse events. But we do know that these low daily and weekly intermittent doses, they seem to be safe. They seem to be overall well tolerated. They can attenuate mTOR1 signaling, which is our molecular target of interest. And most importantly, it can improve a really valuable outcome such as vaccine efficacy, right? So these are all good things. But we have a lot of things that we don't know. So that's great. So there's a lot of positive outcomes there, but we really still are looking to investigate what is the optimal, I don't know if I like that term, but what is the best dose that we can use and what is the best dosing schedule that we can use? We have some precedent based off the data I shared before, but I think we can even do better and make it a little bit more targeted and precision for an individual. What we still don't know if rapamycin can be effective long-term to extend different indices of health span. We know it can work with immune function, but can it work for other important physiological functions such as brain, physical function, et cetera. And then we also don't know how it works with other healthy lifestyle choices. So how does it work if you're physically active? How does it work if you have you're on a certain diet? We still don't know how all these things work out. And so that's something that we're hoping to accomplish in the next handful of years here at UW-Madison. So one study that we are doing, this won't start until next year at the earliest. We're still waiting on official word from the NIA, but we have some good news that it will be funded. This is a phase 1 study. So phase 1 and it's open label. So both the participant and us will know what drug you're on and what dose you're on. So the whole point here is we want to try to find a dose that is safe and effective. So we are going to do a dose escalation study where we will enroll 3 males and 3 females to start at a 5 milligram per week dosing scheme for 6 weeks. We'll measure a variety of different biological outcomes, but most importantly, safety. And so if we sort of start documenting adverse events, that will guide us in how the next cohorts are dosed. If everything is safe and there's a low incidence of any sort of adverse events, then we'll be able to escalate the dose to 10 milligrams per week for the next cohort of 3 men and 3 women. If we still have low rates of adverse events, then we'll be able to escalate to 15 milligrams once per week for the next participant or next group of cohort. And if that still has low incidence of adverse events, we'll just maintain that current dose throughout the rest of the study. If we do start to see an occurrence of adverse events, and we have some really strict criteria that I'm just not getting into today, but if we start seeing an increased rate, we can de-escalate. So if someone gets up to 15 milligrams and we start noticing that they're having more adverse events in the previous cohort, we can de-escalate that dose and go back down. So the study design is one of the best ways to efficiently get people through this study without risking either too low or too high of a dose. So in our opinion, this is the best approach that we can take. We're going to be looking at pharmacokinetics. So pharmacokinetics are basically how the drug is distributed throughout the body. So we'll measure the concentration of the drug at different time points. And then we'll also look at pharmacodynamics, and that means basically how that drug interacts with different molecular target and how it engages with mTOR. And we'll do that in a lot of different tissues. We'll do it in muscle, blood, and saliva. So that will start in 2024. The study that we have ongoing right now is actually using the dosing scheme that the previous study I showed used. So we're using a 0.5 milligram dose per day or a weekly 5 milligram dose of everolimus, right? Because both our mice study and then that immune function study suggest that using everolimus at these low daily or low weekly dosing schemes can be safe. Our primary outcome is looking at insulin sensitivity as measured by an oral glucose tolerance test. So I don't know if anyone's had that done before, but oral glucose tolerance test is drinking a sugary beverage. You drink it and we basically measure how your body handles that glucose challenge. The idea is that your glucose will go up, your insulin will respond, and it will bring your glucose right back down. So the better you do that, the more insulin sensitive that you might be. We're also going to be measuring heart through an echocardiogram. So we'll be able to measure how your heart is functioning because of the data from mice and dogs to suggest that this drug might improve heart function. We'll also be measuring physical function. So we'll be doing a graded exercise stress test to measure VO2 max, as well as muscle strength and muscle power of the lower legs. And last, we're going to look at cognitive outcomes. We're specifically interested in cerebral blood flow, again, because there's data to suggest that Cerebral blood flow is a predictor of dementia and Alzheimer's, and that usually occurs before the onset of those diseases. And that in mice, rapamycin, and in rats, rapamycin can restore cerebral blood flow. So we're going to do an MRI of the brain to measure blood flow, as well as some different cognitive tests. We had originally proposed to look at immune function, but because of just constraints, inflation, you name it, we're going to not do that anymore. So I think there's some sufficient data to suggest that it can improve the immune function. So the idea was that maybe we wouldn't be adding all that much novelty in that space. So those are our outcomes that are related to kind of clinically important outcomes, right? So thinking about your kind of risk for diabetes, dementia, cardiovascular disease, and frailty, and seeing if we can kind of improve those variables to offset that. We are also going to be looking at a lot of different biological processes. We're going to be doing what we call a multi-omics approach. So omics are large-scale profiles of metabolites, which are metabolomics, lipid species, so lipidomics, and then transcripts. So how well our genes kind of respond to this. We'll be able to measure the transcriptomics, and then epigenetics, which is a DNA methylation marker. So epigenetics and DNA methylation have been proposed to be this biological marker of age. So we're going to be measuring whether or not there's changes in the DNA methylation signature, and if it relates to the improvements in the outcomes that we're measuring. In order to do this, we're going to collect saliva, which is easy, just spit in a tube. Urine, that's pretty easy too, non-invasive. We are going to be taking blood draws. So we will take several blood draws to measure, to make these measurements in the systemic circulation. And then last, everyone's favorite is a muscle biopsy sample. Usually the response from the women is, I've had kids, that's nothing, and they have no problems with it. The men usually run out the door. So I will say that I've had numerous muscle biopsies done as a graduate student, postdoc. You get paid to do studies, and so that helped pay the rent when you're a young student. And I'm still able to run my bike. I'm very active, and so it doesn't necessarily feel good, but it's very brief pressure sensation, and then we're done, and you just go on your day. So very low burden from that standpoint.
What is it like with most?
Yeah, so muscle biopsy is, everyone describes it slightly differently. So I think the few common descriptions are a Charlie horse. So you know that cramp, muscle cramp feeling. So it kind of feels like that. Some people describe it as maybe bumping your thigh against like a corner of a table, right? So like that kind of feeling. And then other people describe it as this foreign sensation of something kind of like, people have said, worms or aliens digging in their muscle, because it's just this weird, you just can't really explain it, but it feels very odd, very awkward, and very, it's just very awkward. So everyone has slightly different feelings. I've had a graduate student sleep through one before. I've had someone laugh, so they thought it tickled. And I've also had someone scream at me, and I've also had someone curse at me. So we have the range of emotions when people go through this, but everyone afterwards is usually like, oh, wow, okay, I felt it for a little bit, and then it went away, and here we are talking and having a good time. So I think once people do it, they realize that it's not that bad.
What exactly are you doing?
What are we doing? So we take a little punch biopsy of your muscle. Basically, no, we numb the skin. So we numb any pain. We make a small incision, and then we have a hollow needle. So basically take a core sample of your muscle. And so it's from the superficial area. It might feel that it's deeper than that, but it's relatively superficial, right underneath your skin or fat, depending on who you are. And then we just take a relatively small sample. It's about the size of a green pea, maybe 2 green peas. And then from there, we're able to measure how the mitochondria in your muscle perform. So mitochondria, if you remember, are the powerhouse of the cell. They make basically convert all the food we eat into usable energy. We're able to measure all these biological processes in the muscle, just from a tiny little muscle sample. Yeah.
What studies do you do? You sell, but what tests are you doing?
Yeah, so we actually have some colleagues that have submitted an ancillary study to this. We're gonna hopefully send them blood, and they do a very much in-depth survey of how those immune cells are functioning. And I couldn't really tell you because that's a little bit outside of my wheelhouse. So I'm not terribly comfortable with the immune cell biology. So that is the kind of high level overview of this study. We are going to be starting this summer, so we're going to be looking for volunteers to probably start late summer, early fall. So if there's any interest, we can discuss that more, and I have some contact information to share with you.
Do you do that at home or like
We do this. We have an outstanding clinical research unit at UW Madison, so it's actually in the UW hospital. So when we take blood or we take muscle biopsies, that's all done in the hospital. Yeah.
And is this residential where you live there for a while?
You don't, I mean, you live there for the morning. So for our study visits, the longest study visit would be 6 hours. You get there at 7, you're out by 1. But most of the visits are more like an hour to 15 minutes. So it's pretty quick. There are several visits, I will say that. So that's one of the things we do pay for your time because we understand there's a time commitment there. So if you're finishing this study, if you're one of the individuals that meets this 55 to 80 years of age and you complete the entire study, you get $2,000. And if you don't complete everything, you get a prorated amount, depending on what you do. The beautiful thing too about the clinical research unit is one of the nurses there, she's a research specialist and she used to work for Covance. So she's very good at taking my crazy ideas and making sure they get implemented correctly in the clinic to make sure that everyone's safe and everything gets done appropriately. So the rigor of the studies are top notch. So we are looking at for people who might be insulin resistant or perhaps even pre-diabetic. And there's different criteria we can review. And if you don't know if you are one of those, we can do some tests to make, to try to figure out whether or not you meet these criteria at no cost to you. And the reason we're picking this population is actually more than 50% of this age bracket is already insulin resistant or pre-diabetic. They might not even know it. And on top of the age-related increases in mTOR complex 1 signaling, there's insulin resistance is also associated with what we call hyperactive mTORC1, meaning mTORC1 signaling is elevated. So we think that if we can restore that, we'd have a higher chance of improving some of these outcomes that we've talked about before. Additionally, when you take insulin resistant pre-diabetic individuals, this further increases the risk of the age-related conditions such as type 2 diabetes, cardiovascular disease, frailty, dementia, and then some senescence. And as you can see, all our outcomes are very much related to these disease risks, right? So they're very much clinically relevant. And we know from our preclinical models that rapamycin can inhibit mTORC1 and delay these age-related declines in all of these outcomes. So we will be the first to comprehensively evaluate all these outcomes in a single study in a given population. We're also going to take a young control group. So they're going to do all the baseline testing. So they'll go through everything that the older group would do, but they're not going to do the intervention. So basically, everyone touts this drug as being able to, kind of this healthy longevity. Perhaps you can make people look younger, at least from a biological standpoint. And so we want to put that to the test. So can rapamycin change these outcomes? And if it does it make the older people start going towards that younger direction, if you will? We know we're not going to fix everything or restore everything back to a young person per se, but we want to make sure whatever changes are going on are going towards that young, healthy control group and not the other direction.
Why is the young girl 5 times less than the older?
I'm sorry?
N is 14, this is 72, that's like 5x less.
Yeah, so this N of 72, it's 3 groups. It's a placebo group, it's the daily group, and it's the weekly group. And so that's why. So there's actually 28 per group. And then we have just a half that for our young control. There's more variability as we get older too. So we just need more people to participate in the older groups. And so we call this a double dummy design. So actually every single person that's on the treatment will take a pill once per day and once per week. That way we and you are both completely blind on whether you're on the placebo or the active drug, and whether you're taking the active drug on either a daily or weekly cadence. So it's a pretty sophisticated design. It does mean there's a little bit more pill consumption, but for the sake of science and having a very rigorous study design, it was needed. Great questions. Yeah. Any other questions regarding this study? This is a big one. It's a big undertaking, but I think if we can get a lot of buy-in from the community in Madison, I think we're going to make a really big impact on understanding whether or not rapamycin can have a lot of benefits to healthy aging.
How many people are you looking for?
72. Yeah.
Oh,
Yeah. 72 individuals. Yeah. 72. So, and so just to give some perspective too, it's not 72 all at once. We can't handle all 72 people at once. So this study will be going on for 2 to 3 years, right? So we're thinking more like 20 to 30 some individuals per year, right? So we'll be at this for a while. And maybe even longer, because it seems like every day we learn about a new supply that has a shortage. So just like the rest of the world. So, but just to summarize, if there are candidate drugs or other types of therapies that can be used to help successfully age, then it needs to be able to do so by improving multiple outcomes of physiological function, right? So not just targeting one outcome, hopefully improving things across multiple tissues and multiple systems. We have this working model that inhibition of mTOR1 can be beneficial, while the inhibition of mTOR2 can be detrimental. And so we've designed our studies to hopefully more selectively enable inhibition of mTOR1 and avoid mTOR2 so that we can really move this towards clinical practice in a safe manner. And again, the idea is that we can kind of extend this healthy longevity. If anyone might be interested in participating in the study, this is our study email. You can also contact me. You can look me up on UW-Madison's webpage, but this is our study email, and we have a handful of study coordinators that are going to be working on this study and they can answer any questions you have and also do some screening information to see if you are a candidate that can safely participate. Thank you for your attention. I also want to mention that those studies are funded by the NIH, which means they're funded by you. So those are taxpayer dollars. And so if you do want to participate, kind of reinvesting into the NIH and your tax dollars. So it could be worthwhile. We have a lot of people that help work on these studies. This is not a one-man show by any means. This is my lab group. They are a wonderful group to work with. Brittany, Amy, and Becca are the ones who run our clinical trials on a day-to-day basis. So those are the three outstanding clinical research coordinators that you would potentially be working with. And then we have our folks in the clinical research unit that make this happen in a safe fashion in the hospital.
What is Jake as a lawyer?
Jake, yeah. So one of the things, so we have to get FDA approval because we are not using the drugs as they're meant to be used, meaning we're not using it for kidney transplant, we're not using it for cancer, right? So we are testing this in a different situation. And in order to do that, we have to get what's called an investigational new drug application approved by the FDA. And that was new to me until last year. And Jake is a lawyer that helps with the FDA regulated research. So he kind of held my hand through the process and made sure we had a really good application. So we have one that's been approved, and then for our newer study, it's under review, and we should hear back in the next couple of days.
And what does the RAC stand for?
I don't know. Yeah. Yes.
I believe this drug was used historically as an antifungal drug. You didn't mention that.
Yeah.
I prescribed a lot of rapamycin.
Okay.
Does it still have that indication?
I don't know if people use it as much for antifungal.
I don't use it as much.
Yeah.
Research acquisition.
Yeah. So I'm not entirely sure. I mean, that is how it started, right? It was an antifungal. Yeah, but I'm not sure if it's used anymore.
Well, it's it works dramatically well. I never saw any of the side effects. I probably treated over 100 people.
Oh, wow. Okay.
Just go by the way.
Yeah.
Um,
Was it orally or was it topical that you used it for the fungal?
Here my memory is fading.
Yeah.
And then there's better things than rap. They really aren't.
Are they legal?
In France.
In France.
And there's active work in Romania going on with this drug and
What drug are you referring to? What drug are you referring to? What drug are you referring to? Oh, but you said there was something better.
yeah, but I don't want to talk about it. But the outcome of the dog study. Now, in the dog study, they involved young dogs and old as shit dogs. And what they were doing is they were trying to show there's a way around the FDA, and that they works for a broad general population. Well, what do we know about the outcome of that work?
So the published dog data suggests that it improved heart function, but it most improved those that had some sort of pre-existing age-related declines. So basically, if it was able to fix, but if you don't have anything to fix, then it really didn't do anything. Is basically one way to interpret that.
Because of the flaw in the study, it basically focused on looking at older dogs.
Yeah.
Older dogs, because they obviously are older.
I don't recall the age brackets of the dogs, but they have a new study now. It's called the treating, what is it, triad. So it's treating rapamycin and aging dogs or something like that. And so that's ongoing. That's part of the dog aging project that's housed out at the University of Washington in Seattle. And so they're basically looking at a larger cohort, because that was kind of like a pilot study to some extent. It was a small cohort of dogs, and this was going to be, I think, 400 dogs that will receive rapamycin. And I can't remember the doses or how long, but it should be a very impactful study. Yes.
Yeah, you mentioned that the rapamycin can kind of amp up the immune response. Yeah, it's also used for kidney transplant. And you think that, gee, the active immune system would cause a rejection of the kidney, perhaps. How does that all get balanced out?
Yeah, so it does have immunosuppressant effects, especially when you're giving high doses, and that's why they use high doses for kidney transplant. So it will suppress that immune system from basically rejecting that new kidney. But when you stop rapamycin, that's when they've shown that it can have that rejuvenation effect and improved immune efficacy. So I'm not actually sure if it happens while you're actively on the drug, or whether it's after you stop taking the medication that it kind of causes your immune system to bounce back. Yeah.
In the work where surgeons and their buddies prescribe this stuff like water for decades.
Mm-hmm.
What did you see or notice, or has that inspired anything?
Yeah, so I know that, I was talking to our colleague, Dr. Garg. She is in the nephrology unit, and they don't prescribe rapamycin nearly as much as they used to, because they have to use doses that are pretty high on a frequent basis and have a lot of adverse events. So when you're in those patient populations, when you're prescribing high doses, there's a lot of different adverse events.
Can you get at that data? Because it was very heavily prescribed anti-rejected drug.
Oh, that data, yeah, that data is out there. It's published. Yeah, there's data in quite a few different clinical trials.
Were they informative as to getting good, bad, or indifferent things?
Oh gosh, I don't know about the outcomes, because the primary outcomes would have been related to the disease status. And I think there's a reason why they don't use it quite as much as they used to. And I think that is related to the high doses that have all these adverse events. So in patient populations, at one point, it was kind of like, well, we can risk that, because if we can actually target the tumor, or if we can prevent kidney rejection, if you have these sort of adverse events, it's okay, because it's a means to the end, right? But for aging and taking relatively healthy individuals and putting them on a drug, that risk to benefit ratio just doesn't work out, right? So that's why we try to use these kind of more intermittent dosing schemes to really avoid those effects.
Yeah, it's really interesting that this rapamycin can just, deal with so many different, types of disease. And the superficial, it reminds me like, if you keep true to for all these different kinds of cancer, it seems work for all these different kinds. Is there any kind of similar mechanism that is just kind of a coincidence if they're just kind of general purpose?
I don't know.
Cancer?
Yeah, I don't know how to compare the two different drugs, but I mean, what we know about the mTOR signaling pathway is it has its hands and fingers on so many different processes. So it makes sense if we were kind of disrupting that pathway, that it would have these